All right, we're back. We're looking at case 3. We're trying to find an optimal portfolio of two risky assets without perfect negative correlation. This is probably thus far the most relevant of the 3 cases that we've been talking about. Okay. Here you can think of, let's say you're holding a risky asset. You can think of it as holding a risky portfolio, an index fund, right? And you're looking to add to your portfolio another risky asset. It could be a bond fund. It could be a different mutual fund. It could be a single stock, all right? So you're looking to add to your current risky portfolio an additional risky asset. It's likely that these two assets will not have perfect negative correlation, okay? And so you can see hopefully where we're heading here and that this is a relevant case. Let me show you the math that will get us to the optimal weights of these two risky assets, okay? So we have here, let's let theta equal the expected return of the portfolio made up of these two assets minus the risk-free rate divided by the variance of the portfolio, okay? Now it's important to note, what is in this portfolio? You've got two risky assets. We're gonna call those assets D and E, where we'll let D be the less risky of the asset. I think in a previous video we talked about this, and D is going to be the less risky of the asset. You can think of this as a debt instrument, maybe a bond or a bond fund, all right? And let E be an equity instrument or a mutual fund or an index fund, something like that, okay? So watch what I'm gonna do here. I'm gonna let theta equal this ratio, and I'm gonna substitute in for the expected return of the portfolio. I'm gonna substitute in the expected, the weighted average of the expected returns of the two assets where the weights are WD and WE. Okay, hopefully that makes sense. I've just substituted the sum or the weighted average of the expected returns of the two assets in for the expected return of the portfolio. And down here, I've just substituted in the formula for the variance of the portfolio made up of asset D and asset E. Okay, we've talked about this formula in previous videos. All right. So now what I'm going to do is I'm going to maximize theta subject to a constraint, an important constraint that the sum of the weights of asset D and asset E will equal 1. All right. By now, hopefully, you know how to maximize an objective function subject to a constraint. We're going to take the partial derivative of theta with respect to the weight of the less risky asset. We're going to set it equal to 0, and then we're going to solve for WD. I'll put a star there because that's telling us the optimal weight. All right. I'm not going to show you the math. It gets super messy, but trust me, this is what happens when you solve this problem. You get the optimal weight of the less risky asset to equal this nasty formula here. This is the expected return of the less risky asset times the variance of the risky asset minus the expected return of the riskier asset times the covariance between the two assets. And you're going to divide that by this formula on the bottom here. This is the expected return of the less risky asset times the variance of the riskier asset plus the expected return of the riskier asset times the variance of the less risky asset minus the sum of the expected returns of the two assets in the portfolio times the covariance of the two assets. All right, and of course, the optimal weight of the more risky asset is just going to be equal to the optimal weight. Let me fix that real quick so you have it. The optimal weight of the more risky asset is just going to be equal to 1 minus the optimal weight of the less risky asset. Okay, so these two formulas will give us what we need to help us decide how much weight to put in the more risky asset and how much weight to put in the less risky asset. What I'll do next is I'll provide 2 examples of this using this formula, and we'll go from there.